So today we're lucky to hear Sherrie Wang talk about weekly supervised learning for satellite imagery with applications in crop mapping. And Sherrie is a fourth-year PhD student at Stanford's Institute for Computational and Mathematical Engineering, and she's advised by Professor David Lobel. Yes, so we're very lucky to hear from you, and feel free to start.
Okay, great. Thanks so much for having me. So I guess a maybe more accurate but very long title for this talk would be like weekly supervised learning, unsupervised learning, and transfer learning. So basically, we're in a domain with, instead of having big data, there's only small labeled data sets. So this is really all about looking for ways that we can achieve the results or for the tasks that we care about with as little data as possible or as we have. So a quick outline of the talk. First, I'm going to provide a background on just agriculture, food security, and how crop type mapping fits in, and then what kind of data regime we're in for those people who might not be familiar with agriculture. So then I'll talk about a couple of more established machine learning approaches we've tried, like transferring random forests and then doing some unsupervised clustering in one of our works. And then the second thing I'm going to talk about is a deep representation learning algorithm called TAVEC that we developed last year. And then I'll briefly mention some of the ongoing projects I'm currently working on. So first, quickly, to define food security, the UN, the definition is that it's a condition in which all people at all times have physical, social, and economic access to sufficient, safe, and nutritious food that meets their dietary needs and food preferences for an active and healthy life. So this is obviously a very important goal, and the UN has put it as their sustainable development goal number 2 under zero hunger. So the current state of food security, we've made a lot of progress in the last few decades, but there's still about 11% of people worldwide who go hungry. 1 in 4 children, or 1 in 5 by 2020 is predicted, but still a lot of children suffer from stunted growth. And population is projected to rise globally to about 9.8 billion by 2050. And more than half of that population growth is projected to happen in Africa, which is the continent with the lowest food security right now. So obviously everyone believes that people should be fed, and but on the flip side, there's definitely a footprint to our agricultural activities. It contributes to greenhouse gas emissions, with one study calculating that it's about 20 to 25% of global annual emissions back in 2010. Land conversion is also a big way through which agriculture leaves its mark on the earth. So about 50% of habitable land on earth is used for agriculture, with most of that, about 80%, being for livestock, and then the rest of the 20% being for growing crops. So here is a graphic from the IPCC showing some of the ways through which agriculture contributes to greenhouse gas emissions. So obviously, very important goal, but there are trade-offs. And if we want to grow more food to feed more people, assuming that for now people aren't changing the composition of their diet too much, or like it would be great if people change their diets to more plant-based food, but that currently doesn't seem to be the trend as people, as the middle class grows in a lot of places, for example. So if we want to feed more people without converting too much more land to agriculture, then what we really want to do is increase the yield on the current land that we do have. And one last piece of background that I want to mention related to agriculture is that there is going to be a climate impact going forward. So we know that climate change means that average temperature on Earth is going to increase, and that's going to lengthen the growing season in some places, or in all places really. And for some places that's going to be good, because with a longer growing season, you can grow more food. But in some places that also means temperatures are going to be too high and crops are going to suffer. There's also going to be changes in precipitation patterns, so there will be more extreme events like more droughts, but also more rainfall more intensely in some places, so that's going to lead to also more floods. And the IPCC has also forecast that the poorest countries are likely hit the hardest. So there's a graph, or there's a map here to show some of the countries that are projected to be hit hardest versus benefit the most from climate change, purely from an agricultural standpoint here. Okay, so how does AI fit into this whole picture? There's a few avenues through which AI currently and going forward can help agriculture. So one is on-farm automation. For example, automated tractors, sowing and harvesting. There's soil and crop monitoring. So there's a lot of startups working on, say, flying drones or using satellite imagery to look at the plants in a field and figure out which parts of your field are doing well or might be suffering from maybe some disease or pests, or needs to be irrigated more or less, or fertilized more or less. That also is related to precision agriculture. So one of the environmental impacts of agriculture is too much. When fertilizer is used too much, or pesticides and herbicides are used a lot, they can leach into the environment and have really bad consequences for the surrounding ecosystems. But with precision agriculture, you're only spraying or applying what you need. So the idea is there's less runoff, and also the farmer can save money by not spending as much on input that they don't actually need. And then there's also predictive analytics, so trying to forecast, for example, what the yield is going to be in a growing season. And so today, what I'm going to be talking about is more related to the crop monitoring aspect and also predictive analytics. So what crop type mapping is going to be able to allow is better yield forecasting. And then a separate piece of background for those of you who are not familiar with remote sensing, what that refers to is using satellites or airplanes, so remote sensors to gather information about what's happening on Earth. So some benefits of this technology are that once your satellite is up there, or once you've invested in a drone or airplane, the marginal cost of acquiring more data is pretty low. It's also, a lot of it is quite accessible to researchers and people in industry. So a lot of this data, especially the satellite data, is publicly available. There's more and more private companies, CubeSat companies offering very high resolution data, but usually you do have to pay for that. But it's definitely out there. You also get real-time or near real-time monitoring. So a lot of these satellites either capture at every location on Earth on a daily basis or on a weekly basis. And then you have increasingly high spatial resolution. So we're talking about maybe 10 or a couple tens of meters per pixel in an image, or the really high resolution stuff would be like sub-meter resolution. And you also are able to get global coverage. So a lot of places, it might be difficult for people to travel to on foot, either expensive or even potentially dangerous. But with satellites, you are able to take pictures everywhere. I think maybe some politics prohibiting certain areas, but mostly it's global. So the ideal pipeline here, and feel free to stop me or ask any questions if any of this isn't clear yet. But the ideal pipeline here is you get this remote sensing data. We have developed a lot of computer vision, machine learning algorithms, currently mostly for natural images, so images that people like take on their cameras and phones, but also applicable to remote sensing data. And hopefully through this combination, we can get some very large scale insights that can help us understand the current state of food security and how we can increase yields and things like that. So crop type mapping specifically tries to answer the question, where are particular crop varieties being grown? So varieties like maize, soybeans, rice, wheat, etc. And then once we have that information, that can enable us to answer more questions that are very important for security, such as what will the crop yield be this season for a particular crop? You can look at that using satellite imagery, and how have farmer decisions changed over time? For example, how did a change in policy incentivizing or subsidizing, say, corn, change how farmers choose like which crops to grow? What management practices optimize returns on inputs? If you have some data either collected on the ground or something that you can tell through remote sensing data like irrigation, for example, you can try to understand what's being irrigated and how do those management practices impact what the yield is, and then what ultimately the profit that the farmer gets. So as I mentioned in the very beginning, this entire field is constrained by a lack of labeled data, especially in parts of the world where food security has still been elusive, and having this data would be very useful for studying a lot of these questions. So really the amended diagram would be, with remote sensing, we have a lot of imagery because it's constantly coming in from the sensors, but it's not labeled. So we don't have a lot of labels, and we know that a lot of the computer vision techniques, the state-of-the-art techniques today involving convolutional neural networks, and especially very deep networks, they do need a lot of labels to be successful. So this talk is going to be about trying to address this question of crop type mapping, working with the small quantities of data that are out there. Any questions before I jump into the first part of the first project? Okay, so the first project I'm going to talk about is called Crop Type Mapping Without Field Level Labels, Random Forest Transfer and Unsupervised Clustering Techniques. So this was published in Remote Sensing and Environment just earlier this year. And the problem statement here is we're going to assume that we have a binary crop mask, which means we know where cropland is in the world. This is not always true everywhere, but this is relatively easy to get because cropland looks pretty different from forest and from water and from urban areas. So it's not super hard to create this from your computer and using like Google Maps or something. LANDSAT images. LANDSAT is a particular satellite publicly available run by NASA and the USGS. And then we are assuming here for the moment that we don't have labels of particular places like GPS locations of what crop is growing where in a particular season. So when I talk about the supervised learning transfer, we are going to use labels from either other places nearby or a different year. But we're going to assume for this particular year that we care about, there are no labels in this region. And then, but what we do have is we have aggregated crop data. So that means some sort of usually government collected data For example, in the US, in Illinois, it could be county level data. So for the Lake County in Illinois, you know that 8,500 acres or hectares, I'm not sure what this unit is, of that area is growing corn, 8,900 is growing soybean, and so on. So oftentimes you have this aggregated data, and their absolute numbers around the world may not be very accurate, but often the ratios between crops can be still quite accurate. So we really wanted to know, can we use this information to help us do our crop type mapping? And the study area here, I know we talked a lot about so far about not having data. So to understand how well these methods might do, we first started in the US Midwest. So this is a place where there's really good data. And what you're looking at here is what's called the cropland data layer, which is compiled annually. And every different color means a different either land cover type or a different crop type. So here you can see a lot of yellow and green in the Midwest, and yellow corresponds to corn pixels, and green corresponds to soybeans. So this cropland data layer is a 30-meter raster. So for every single LANDSAT pixel, there is a label that the USDA has given it, whether what they think is growing there. And the satellite data we're working with is LANDSAT, as I mentioned, and LANDSAT is 30-meter resolution, 16-day, each satellite is 16-day frequency. So together there's 3 of them. LANDSAT 5 has been discontinued, but basically it'll be somewhere more like on the order of a week. Every week we have an image. And then there are 7 bands in this satellite. I guess I have listed 6 here, 6 of the most important ones, and they're the standard red, green, blue that we're familiar with when we look at images. And then there's also near infrared and then 2 shortwave infrared bands that are very helpful for classifying vegetation. So the overview of the process that we're going for is something like this. So first we want to start out with some sort of LANDSAT imagery. Here it's just visualized in RGB for some fields in a county in Illinois. Then we have the CDL pixel level labels that we consider ground truth. They're definitely not perfect, but they're very good. They're like over 90, 95% accuracy in most places in the Midwest. So we're going to use this either for training when it's a transfer learning technique, or just to validate when we're doing clustering. So the way we're going to extract features, I'll talk about it in a second, but it's a harmonic regression.
Quick question. Sorry, I didn't get, what are you using for the ground truth?
The ground truth is something called cropland data layer. So this is data that is available currently every year in the US for every single LANDSAT pixel. So this is like, we obviously don't have this quantity of data in places around the world where we actually want to be applying these methods, but the US is a really good place to start because of the large quantity of validation data, basically. Okay, so and then
a question.
Yeah.
I'm wondering, have you processed this image data? Because for the remote sensing, like for the satellite data, there must be some images with lots of clouds or like some distortion. So I'm wondering, how did you select or how did you process this kind of data?
Yeah, so good question. That's definitely a big concern with satellite imagery. So LANDSAT, they take their raw images and it's processed very well, like they calibrate it. So we're using LANDSAT surface reflectance. So that's after they've like accounted for, say, atmospheric effects. And then we also, LANDSAT has a really good cloud mask. So we just use their, the cloud mask that's built into their product. And we remove all the pixels that are labeled as cloudy by the in-product cloud mask.
Thank you.
Okay, cool. So, okay, yeah, so last couple panels here are what we're going to do with the machine learning methods. So we're taking the features that we extract from panel C, which I'll describe soon, and then we're feeding them into here either random forest or some sort of clustering algorithm to recover what those crop labels should be. So for the feature extraction, if you look at the panel on the left here, this is what like a raw LANDSAT reading at one particular pixel is going to look like over the course of an entire year. So here I'm showing on the y-axis something called GCVI, which is a vegetation index. It's like something that people in the remote sensing community have figured out. If you calculate some combination of the raw bands that I showed in the LANDSAT slide, GCVI corresponds really well to like vegetation growth. And then the x-axis here is just days of the year, or months of the year. So you can see what you're looking at here is that the crop is sown sometime in May, and then it starts to grow. It gets greener and greener, and you can see this on GCVI. It hits a peak, and then people harvest it, and that greenness goes down again. So what we're going to do to try to extract features from this time series is just a Fourier transform. So within orders here. So in this particular case, we're using n equals 2. So we're going to have 6 coefficients from each curve. And that's how so there's going to be different numbers of readings at each pixel, depending on, how cloudy each place was, and then how many times LANDSAT passes over each place. But every point is still going to have 6 coefficients once we do this fit. And if you look at the graphs on the right, that's showing the green curve is soybean, and then the blue curve is corn. So you can see what is separating these crops, at least in this Fourier space. You can see that the corn curves are usually a little bit lower in amplitude, and then also earlier than the soybean ones. So these sorts of differences are going to help us differentiate crop types. And then the machine learning methods we use here are just very well-established ones that the remote sensing community uses a lot, and they're very familiar with it. So here we're trying to see how far we can extend these in space and time. So I'm not going to describe these here because I think probably this audience is very familiar with them, but the supervised learning method we use is random forest, and then we tried 2 unsupervised learning methods, k-means and a Gaussian mixture model. So, oh, that's a nice animation. Okay, next slide. So random forest, this is a lot of bars that you're looking at, but I'll just explain what it means. So on the left, we tried doing applying a random forest trained on one particular state, and we applied it to the 8 other states. So there's 9 states in the Midwest in this study. Illinois, Iowa, Indiana, Nebraska, North Dakota, South Dakota, Minnesota, Wisconsin, and Michigan. So what you can see when it's applied to a nearby state, it can do really well, basically if it's similar to that state, and we will quantify what similarity means in a second. But if it's very different, it's a very different state, for example, North Dakota is like very different from most other states, it's going to do really poorly, which is not all surprising, but we'll see in a second how to quantify that a bit more. And then if we transfer random forest across years, there's also similarities and differences between years. So 2012 was a very dry year. So when you apply any model trained on in 2012 to 2012, you're gonna usually see worse performance. And to see how you might be able to know ahead of time, like how well transferring the supervised method is gonna work, we looked at what happens when you train this model in one region with a particular GDD, which stands for growing degree days. And GDD is it's it's a metric for how much thermal time a plant is exposed to. So thermal time is like degree days. So plants need a certain range of temperature to flourish, and it needs to accumulate enough of those temperature days in order to grow and have a like a high yield and stuff. So basically, if two regions are similar in GDD, then they're roughly, to the first order, their growing conditions for plants are relatively similar. So this is especially true in temperate regions like the US, where temperature is a limiting factor for growth. The sort of relationship that you see here may not hold as much if in another place that's, say, precipitation limited instead of being temperature limited. So what you're seeing here, there's a lot of these graphs, but if you just look at 1 year, for example, 2016, what this is saying is if you train on a region with a particular GDD, then if you apply it to a region with a similar GDD, then you can expect to get very high accuracies with this supervised learning method. And then if you apply it somewhere beyond a certain GDD difference away, then that really is not going to do well. And then when we did clustering, we found that, again, if you just look at 2016, for example, we can recover accuracies almost as high as a random forest method using just a Gaussian mixture model on the harmonic features that we talked about in some states, and then in other states it totally fails completely. So the process here is we cluster on the harmonic coefficients, and then using the aggregate crop data that we mentioned in the beginning in the problem statement, those can help guide which clusters get assigned to which crops. So you use like how much of each crop is grown in each county and state, and then so you can use that information to assign clusters to crop type names. So then the question is like, why is it doing so well in some states and not in others? And where can I expect, if I'm going somewhere else in the world, where can I expect an unsupervised method along with aggregate data to work, and where can I expect it to work? So this graph on the left, I think, gives some clue as to what regions you might be able to use such a method and which regions you might not. So if you look at the entropy of the crop distribution in each of the places, this is broken down by state, and then within each state, we're breaking it down again by GDD. So that's why there's a bunch of points for each state. If you look at the entropy of the crop distribution, if the entropy is really high, aka there's a lot of different crops growing in a particular region, and you're trying to do clustering with like a very large K, then it's going to be on average like really pretty difficult to recover all of those crops. So entropy is correlated with clustering accuracy with an R-squared of 0.6, which is quite high. So on the right, you can see two examples of two such regions that we applied clustering. And the top one, it just totally didn't work. You can see there's a lot of different crops growing here, and trying to do clustering with like K = 7 or something like that does not work. But in many places in the US, people are growing mostly just corn and soybeans, and so the entropy of that distribution is very low and the accuracy is very high. So, I mean, you might be wondering how much of the world really looks like the bottom graph in panel B, and the answer is really a lot of places where agriculture is quite industrialized. So that this might mean this method is going to be difficult to use in parts of the world where agriculture hasn't been so industrialized. Okay, so to summarize, we can create crop type maps with pretty high accuracy without in-season field data in some regions of the Midwest. Fourier transform coefficients are pretty good at distinguishing crop types. Random forest classifiers can transfer well across regions with similar growing degree days, and then the Gaussian mixture models do cluster crop types accurately, but only in low crop diversity regions. This is some of the learnings from this study in the US. Any questions before we go on to another work?
How did you pick to use those features provided by LANDSAT to train on? Did you try using something like a convolutional net to extract features for you?
So I am currently working on a project where I try that, and it's doing a little bit better than the random forest with kind of these engineered Fourier transform features. But because the raw data itself is very noisy, and in a lot of places we don't actually have that many labels to learn the features very effectively. I'm not seeing that it's a lot better than just extracting it using a Fourier transform, but they're definitely comparable.
Okay, thank you.
So you mentioned that for each pixel you have like 6 features like RGB and infrared,
Yes.
and
Well,
to act God. So later on you use the coefficients of the Fourier transformation. So and that seems that that would only depend on RGB or like how do you compute that number? And I think the later on is basically you are so all the classification depending on like the coefficients of the different frequencies.
Wait, sorry. I think I missed the first part of your question.
So basically, for that signal, how did you compute that? You said it's some kind of transformation of the raw feature. Yeah, this one.
So we're fitting this curve with n equals 2 to all of these readings for the entire year for every single LANDSAT band, and then also a number of vegetation indices that are very commonly used in the field of remote sensing. So there's 6 coefficients per band or vegetation index, and then we're using, I can't remember exactly how many total, I think it was like around 13-ish vegetation indices and bands. Does that answer your question, or?
I think I'm just wondering, like here, like the value you're using is GCVI, right? And
Yeah.
the previous the feature provided by the sensor is like RGB, and the features you provide. I mean, I'm just wondering how you transfer the transform these bands to that value.
Good question.
Oh, I think GCVI is it's not a linear combination. It's some non-linear combination of these bands. So it's just something that has been developed over decades in the remote sensing community.
Okay, sure.
Yeah.
I don't actually remember the formula off the top of my head, but there are actually a bunch of these vegetation indices that are kind of useful for different vegetation characteristics.
Oh, by the way, when you use clustering, do you consider like the spatial relationship between different pixels?
For this particular study, no. And also with LANDSAT, it's already very, well, it's considered a medium resolution satellite, but for purposes of mapping crop fields, it's relatively low. And so there's not, I think there's something you can gain probably from using LANDSAT with spatial context in the US where the fields are very large, but in different places around the world, one LANDSAT pixel is going to be oftentimes like bigger than a field in some parts of the world. So here we're not using anything spatial, but in the next study and then in current ongoing work, we are using like CNNs advantage of that spatial context.
Right, okay, thanks.
Hi, Sherrie. I have a question. The same slide with time series for the crop.
Yes.
Why does it look like January has a high vegetation index?
Oh, that's just an artifact of the fit, which is trying to minimize the residual sum of squares between the curve and the points, which are mostly collected from, you can see like March to December. And January actually doesn't have that many points because it's either very cloudy because it's like snowing in these places, or there's snow on the ground and Landsat masks out cloud and snow. So what you end up with is not very many points in January that you're trying to fit to. So as a result, it kind of goes crazy there without any consequences in the fit.
I see, I see. Okay, thank you.
I have a question. Hello, can you hear me? I have a question. Can you hear me? Can you hear my voice?
Yes.
Okay, just make sure. Just so, like I just want to confirm that. So the methods you're using is you use the change the curve of peak of the like the RGB or the band those band information from satellite to fit a curve of the GCVI for most area, and you also have a ground truth for this kind of GCVI curve for each different crop type. Then you try to match them to do this kind of crop type mapping. Is that you are doing?
So there's no ideal curve here. This is like, all of it is like statistical. So we are fitting these curves to every single band and then a bunch of vegetation indices at every pixel in the study region. So every pixel has its own set of like 60 something features.
Yes.
And then for the random forest component, we're saying we're going to train on labels from that massive ground truth data set that we have called CDL. In a nearby state or a different year.
So your ground truth is like a label for each pixel. Say this pixel absolutely corresponds to corn or soybean. Is that your label?
Yeah, it's provided by the USDA. Yeah.
Okay, I see. So GCVI is like some index that can compute automatically, as Junwen mentioned. Asked your first question.
Like, for example, I don't remember the formula for GCVI, but for example, it would be something like the red band value minus the near infrared band value divided by the red band value. Like that.
Okay, I see.
One vegetation index that like someone has come up with.
So it's like you are using this kind of index, like time series change of this index to as a feature to learn the mapping between this kind of feature to the crop type, right?
Yep.
Okay. Thank you.
I have a question.
Yeah.
So I'm wondering, do you think the geomorphology is important for this kind of like images? Because I think if the altitude and like if there are some mountains, it may affect the like reflectance or other things. So how do you think about this?
Yeah, definitely that is a factor. In the Midwest is extremely flat, and here we didn't really consider those other attributes. I think one thing is that built into some of these products, they tried to correct for differences in reflectance angle and things like that. So we're more relying on them to provide that satellite product with the appropriate corrections. We have also tried adding, not in the US, but in other parts of the world, adding features like altitude as one of the predictors. Yeah.
Okay, thank you.
Yeah, I have a question. So here, you are still using the NAS crop data layer as your labeled data, right?
Yes.
For your training. So if you want to apply this algorithm to Africa, where you don't have such kind of data set for as label for training. So how this method could be applied to like in practice, like real?
Yeah, so, I mean, usually what happens is people go out in the field in countries without a really nice data set like NAS, and then they do some field work and they have labels for like 1,000 fields or something. So one thing we try to learn that is a little bit transferable is like how far out could you apply, apply those, a model trained on those 1,000 fields, where might you expect it to work well still? And where can you trust your results? So yeah, you're definitely right that it's much more limited in other parts of the world, which is why we also tried the second component of unsupervised clustering, because that, if that worked in regions with, well, higher crop diversity, then that would mean you could apply it also to these other places, possibly where you have, often you have aggregate data.
Yeah, okay.
But yeah, there's definitely, as you can see, there's limitations to both of these methods.
Yeah. Yeah, I have another question. Say you said you use a number of different bands, either raw bands from LANDSAT or the derived vegetation index, all different different variants of vegetation index from those bands. So how redundant these bands are, because they are basically calculated from the same like 7 bands, right?
Yeah,
so
some of them are very highly correlated.
Yeah.
We did do a feature selection stage, and we were only, in the very final results, we only are using a subset of those 60 features, because yeah, like you said, a lot of them use like near infrared, they use a lot of the same bands, so they are super highly correlated. Yeah.
Okay, so in that regard, in terms of like feature selection and so that part is still like more supervised, right?
The feature selection was done in a supervised manner, yes.
Okay, yeah, okay, thank you.
Yep. Okay, cool. I think the second study is a little bit different, and if there are no more questions, I'll just jump into this. So AVEC is the name of this algorithm that we came up with, here we're using CNNs to do unsupervised, or really weakly supervised representation learning for spatially distributed data, and this was presented at AAAI also earlier this year. So the motivation here again is that, as we mentioned, there's a huge amount of data, small amount of labels, and it's also hard to do, to apply some of the state-of-the-art deep learning methods trained on natural images and then transfer them to satellite imagery, because as we saw, imagery is often multispectral rather than RGB, and then also the features themselves, like satellite imagery doesn't look that similar to natural imagery, so you can expect the features to be quite different as well. To motivate AVEC more, if you look at this image on the left in the blacked out box, and think about which option, A, B, or C on the right, belongs there the most. This will illustrate kind of the motivating principle behind AVEC. So if you're looking at this and you think that C belongs there the most, that would be correct. And this illustrates what's called TOBLER'S first law of geography, which states that everything is related to everything else. The near things are more related than distant things. So taking this very simple and intuitive law, we can see that one reason you might want to learn a representation that is different from just like say RGB or spectral representation is that there may be high within class variation for things that on the ground are actually similar to each other semantically. So for example, you can have crops in different orientations, you can have them at different seasons so they look different in color, or just they might just be different color soil, for example, or different building colors. And what we want in this project was to learn a new representation space, not just RGB or spectral space, where things that are semantically similar to us as humans become close to each other in this new representation space, but they're far away from things that are semantically dissimilar. And to learn this, we're going to use the TOBLER'S law concept. And the inspiration for this work was Word2Vec, which I think most people are familiar with nowadays. So Word2Vec says that words that appear in similar contexts acquire similar embeddings. And here the analogy is where Word2Vec is learning vector representations for words. We're learning vector representations for tiles of satellite imagery, hence Tile2Vec. And the analogy for a sentence, which is the context of a word, which determines which words are near which other words, the context for a satellite tile would be a larger satellite image. And the example data set, one of the example data sets that we ran this algorithm on is the National Agriculture Imagery Program aerial image, in this case in Central California. So here you're just seeing which region in Central California we used. It's near Fresno, California. There's a lot of crops here. You can see all the crop fields. They're pretty diverse in what crops they're growing in this region, actually. There's a lot of grapes, a lot of almonds, and you can also see the city of Fresno. It's like the big grape hub. So again, we're using CDL here in California now as the land cover ground truth to eventually validate our methods. Here's just some tiles sampled from the NAPE large data set, showing some of the top classes. So again, grapes, almonds, there's like various urban areas and some other crops, and then like kind of just bare dirt. Okay, so what Tile2Vec is doing is it's saying we want to make, similar to Word2Vec, we want to make words that are appear together a lot, have similar representations. We want tiles that appear next to each other, right, geographically next to each other, to have similar representations. We want tiles that appear far from each other to have more different representations. So we're gonna, the terminology we're gonna use is anchor tile for really the first tile that you sample from the image at random. Then you have a neighbor tile, which you sample from within some radius of the anchor tile. And then you have a distant tile, which you sample from outside of that radius. And here, this is like a toy example on a very small patch of the overall data set. We have 3 triplets that we've sampled here, 0, 1, and 2. And you can see the 0 pair, the first one came from a parking lot, the second one, so the anchor image is dark blue. The, actually, I think the anchor image is the light blue, and then the neighbor image is the dark blue, and then the distant image is the red. So you can see with the labels, these are CDL labels on the right half of the bottom image. You can see that anchor and neighbor often come from the same CDL class in this case, or semantically similar class. And then the anchor and the distant come from oftentimes different classes. So sometimes you are going to get things that are where anchor and neighbor are different and anchor and distant are the same, but on average, TOBLER'S law of geography is going to hold, and so there's going to be some signal in this data set where most of the time anchor and neighbor are similar semantically. So that's going to be our learning signal. So what we do is we feed these tiles into a convolutional neural network, which we denote here by F sub theta. So parameterized by theta, and we're gonna, at the end, this neural network spits out a vector representation of each tile. So that's F theta of tile anchor, TA, for example. And the loss function that we're training it on is, we want the anchor tile and the neighbor tile representations to be similar or close together in their 2 norm. And then we want the anchor tile and distant tile difference to be large in the 2 norm. And then we also have this margin, which is saying, the margin M is saying if you make the anchor and the neighbor close enough and the anchor and the distant ones far enough, then like at some point we're satisfied with this and you don't have to push out the distant tile anymore. And then we're also, there's also a rectifier here. So that's the subscript last time. Okay, so, and we also, I think, I didn't mention this here, but we added a regularization term on the size of the representations as well, because we don't want the algorithm to satisfy this loss function just by like making the vectors really, really big. So that's why we added also a regularizer. Okay, so the land cover classification task that we're doing is very similar to what I mentioned before. It's basically trying to predict the CDL labels of each tile. And here, the data set split that I'm mentioning is just because tiles can be, there's like spatial autocorrelation in tiles. So they, like ones that are very close to each other look very similar. And if we split them into separate train, validation, and test sets, ones that are really close together, then we can inflate our metrics. We don't want that. So we split them by these very large spatial chunks. That's just what this diagram is showing. So we compared tile to vec features. So tile to vec is an unsupervised, or you can consider it weakly supervised by geography feature extraction algorithm. And so when we do the class, the crop class prediction task, we're feeding those features then into some sort of classifier with a relatively small number of labels. So that's either going to be random forest, logistic regression, or here a multi-layer perceptron. And across all of these classifiers and across two different dataset sizes, we're seeing that the features extracted by tile to vec are doing better than features extracted by an autoencoder, pre-trained ResNet 18 features, PCA, ICA, and k-means. These accuracies, I guess they look low, but it's for like a 20 class classification problem. So it's much, much better than random. And I think one of the coolest results we got was that actually when you use tile to vec features that were trained with 100,000 triplets, but no labels, and then you use here, the graph here is showing a varying number of labeled examples once tile to vec has been trained. So tile to vec is the orange line. And we're comparing that with end-to-end supervised learning using ResNet, Inception, and DenseNet with a number of labeled examples. We're seeing that the tile to vec features with a logistic regression classifier outperform the end-to-end CNNs all the way up to like 20,000 labeled examples or so, or maybe 50,000 labeled examples. So basically you'd have to have a very large label data set before you're learning features through this end-to-end network that are better than tile to vec features. Some more qualitative experiments that we did to show what's actually happening in the latent space of tile to vec is we did a linear interpolation in the latent space. And what that means is we pulled out, in this example, a very clearly rural tile. So that's like just something in the middle of a crop field. And then we pulled out an urban tile. We calculated their tile to vec representation, and then we did a linear interpolation in that representation space from rural to urban. And then at each point along the interpolation, we grabbed the 5 nearest neighbors. And then now we're visualizing what those original tiles were. So you can see it's going from more rural to more urban at each step. So you can see that this representation space, there's some actual linear structure in this representation space. And I think this is the last slide. Yeah, okay. So the last experiment we did qualitatively was we did some arithmetic in the latent space as well. So we took the representation of a rural tile in New York City. So this is a different data set than the one I just mentioned. This is LANDSAT, back to LANDSAT, 3 cities, New York City, Boston, and San Francisco. And if we take a New York City rural tile and then subtract from that a SF rural tile and then add a urban SF tile, the 3 nearest neighbors to that arithmetic in representation space are 3 New York City urban tiles. And then similarly for Boston urban and San Francisco rural, urban and rural. So to summarize, because I think there's only a couple minutes left, so right now, geospatial analysis lacks representation learning methods that allow us to do better with fewer label points. So tile to VEC is extending this idea from word to VEC, that close things should be more similar than distant things to spatially distributed data. And then we show that the representations improve performance in downstream classification tasks, for example, crop type mapping, and also allow for some latent space arithmetic. And very quickly, current ongoing work. I'm doing crop type mapping in Kenya and India right now, using the methods that we just went through, and also some new things that we're developing. And in this case, it's on Sentinel-2 satellite data. We're looking at deep generative models for representation learning as an alternate or complement to VEC. And we're also looking at weakly supervised cropland segmentation when you only have image level labels. So yeah, that's everything I've got.
I have a question.
Yeah, sure.
For the Sentinel satellite, I think it only it was launched in 2015, and it's like only 3 years. Is there like enough data right now, or like how do you think?
So Sentinel-2 is not, yeah, like you said, it's not that great for 2015.
not going to.
But there's quite a lot of data now for 2017 and 18, and then in Kenya and India, the labels that we have, which are limited, they actually come from 2017 and 18. So it matches the Sentinel-2 profile pretty well, and also Sentinel-2 has the advantage of being 10 meter instead of 30 meter.
But if you are looking, also looking at the temporal pattern, so I think you may need like data from 7 or 8 years. So do you think that, like the only 2-year data is not enough, or?
So the temporal data that we need, like in a particular growing season, I guess you can't really assume that the crop is the same at a particular pixel across growing seasons. So we really only look at the time series within a particular year, and there's like say like 50 Sentinel-2 readings over these places that we're at in Kenya, for example, every year. So that's more than enough points to fit a curve or to do some sort of convolution over it.
But if you have multiple years data, it will increase the training accuracy to some extent. Like 5-year data? Or?
Definitely having more data is better. But in this case, we only have labels in 2017 and 2018 anyway. Mm-hmm. So we don't have actually labels going back before then.
Oh, okay. Thank you.
Yeah.
Just 2 quick questions.
Yeah.
First, what is the dimensionality of your feature space that you're doing with?
In this case, it was 512.
Okay. And second, I was wondering, it looks like you're using L2. I was wondering if you tried other comparison methods and found this to be the best, or?
So this triplet loss is fairly well established in literature. So we just kind of went with this triplet loss with a L2 norm. We haven't tried other norms.
Okay, thank you.
Do we have more questions?
No.
Otherwise, I think this was pretty exactly 1 hour.
Yeah.
So that's, thanks, Sherrie.
Yeah, thank you guys. This was a lot of fun.
Yeah. Awesome.
Thanks for your questions. Yeah, they definitely raised some good points.
Okay, so then I believe the next talk will be in 2 weeks. And otherwise, I'm wishing everyone a nice weekend.
Yeah, you too. All right.
Yeah.
See you guys.
Bye-bye.
Bye-bye. Thank you.